the fifth talk of what is. So today we have Soumya Dasgupta. He will talk on what is stable homotopy, and his interests are primarily on symmetry. Over.
Thank you for the introduction. So the title of the talk is what is stable homotopy, but had it not been the what is series, I would have liked to call it the music of spheres. And don't thank me for the title because it was given by Ramadan. So there's a nice story actually. So Ramadan has a wonderful book on stable homotopy. It is called Complex Cobordism and Stable Homotopy Groups of Spheres. So he wanted to give the title the music of spheres, but his publisher said that you shouldn't be so confident with the librarians because they are not so sensitive and they might put your book in some other line. So I hope there are no librarians over here. Okay, I expected a much better answer on that. So, okay, when I was preparing this talk, so I realized that I might overshoot my time, but let's see what we can do. So, we start off with some constructions. Is this visible or should I change? Change. So I got some constructions which we will need throughout the talk, so just to get through with the notation. So the wedge product, I think this is something we all know. Okay, I should mention one more thing. So we will be mostly working on the category H top, that is topological spaces up to homotopy, or HCW, that is CW complexes up to homotopy, and math being CW math. The wedge product will be given any two base spaces x and y. We will define the wedge product to be you just identify the base point of both the spaces. And now we have got the smash product. So once you have defined the wedge product, you can define the smash product of x and y as you take the Cartesian product and you quotient out the wedge part. Next, suspension. So suspension, we all know what it is, but over here we will be actually considering reduced suspension because we want to have a base point. So it is simply you take the space x and you smash it with s naught. Just to give you, so if this is your space x, you can give s1 as a interval and you identify both the endpoints. So if you do that, then the smash product is simply you take the cones over x, and if this was your base point, say x0, you identify this kind of. So that is the smash product. And the smash product gives you a functor from h top to h top. So given any map between x and y, you can find a map between the suspension of x and suspension of y. And lastly, we have got loop spaces. I should call it loop space. Let's just call it loop. So this is denoted by omega of x. It is the collection of all those maps from S1 to x. So if you have your space x, you are just looking at loops which are inside x, and the base point is going to be the constant loop at the base point of x. And with that, you have got the suspension loop at junction. So given any space x and y, there is a natural isomorphism between these systems. The most natural one that you can think of between these two spaces, that is going to be the isomorphism. And by square bracket, I will mean homotopy class of maps between these two spaces. So with that data, we can now define what are called homotopy groups. So maybe I should start with this slide. So homotopy groups are just natural generalization of the fundamental group. You given any space X in say H top star, so it has a base point and it is a topological space, and you define the the homotopy group Sn by n of x to be the homotopy class of maps from Sn, and you define E1 to be the point 1 at the first quadrant and 0 other way to the base point. So these are all the maps which are from Sn to x and take the base point E1 to the point x. This is for, and we can define for n greater than equals to 0. For 0th case is just going to be the path components. For n equals to 1 it is the fundamental group, and for higher values of n it is called the higher homotopy group of a space. Y group, so we won't be proving that, but just to give you an idea why this forms a group. Okay, before that let me just give another definition. So you can also define relative homotopy group. So we have given subset A of x, A sits inside x, and say you have a base point x. So the base point should be in the subset. And you have got the path space. So x superscript I means all the paths from x from the interval to x that start at the base point x naught. And you have a map, so omega going to, so any path omega, it goes to its endpoint. You can then consider what is called the homotopy fiber of say this inclusion. This is another, so this is a pullback of this diagram, and you define the relative homotopy group to be pi n minus 1 of omega, pi n minus 1 of fi. Fi is a space, and you can define the homotopy group. Okay, when the base point is going to be obvious, I will leave out the base point. The base point over here in this case is of course the constant at the base point. And you do this for n greater than equals to 1. Otherwise this makes no sense. Now why does it form a group? I won't prove it, but just to give you an idea. So say you have got two maps over here from this set, and the basic idea of giving an operation, we want to give an operation between those maps. So you have got your Sn. You consider the pinch map, so the map that pinches the equatorial circle, equatorial sphere. You will get two copies of sphere after this. And to each of this part, you apply, say, so, okay, that should start with F and G. Okay, so when I write this, this means the representative class in the homotopy group from pi n of x to then the representative F and G. This is the pinch map, and you apply F to the that component and G in this component to get your space, to your space X. This is a well-defined map, and you define the F plus G as the homotopy class of this composition. So, F oh, okay, I should have used that word. Never mind. So this is the group operation that we want to define on our fundamental group and the homotopy group. You can check that this is the operation that we need. Very sorry for this extra. Now we will look at another definition too. So you say x to be n connected if pi k of the homotopy groups are trivial for indices less than x. Now the problem with homotopy groups is they don't have accretion property. So if you have read homology theory, you will see that homology groups have accretion property, and that sort of helps you in the computation. The accretion gives you long intact sequences in homology, it gives you mere pretorius and all those things. But in homotopy groups, you don't have that thing. You have a alternative that is taken in this theorem, but it is up to a certain limit. It is not always true. So that basic problem, like it forces us that the computation becomes difficult. So say you had a space A, subspace A, and set inside X, and you take a quotient. So if you are familiar with homology theory, this will give you a long index sequence in homology groups. And this sort of helps you doing the computation. Like if you choose a suitable A and you know the suitable quotient, you can find out X. But in homology groups, you don't have this. You have long index sequence for pairs, but in general, you cannot have such thing. And to resort we have for what is called long exact sequences when you have a fibration or a fiber bundle. Basically, in this case, the fibers, they are not homogeneous. So, leaving aside we said in the point A, all other points of fibers they are single point, but in A points have representatives in the whole space. So, to resolve that, we will consider spaces whose fibers are sort of homogeneous, and there we are the following theorem. So let P form we consider a fibration, or in general, if you are not familiar with fibration, you can consider fiber bundle, meaning that each of the fiber is homogeneous and they have local duality. So, and P is path connected. Then you have a long a long sequence. Let me call F to be the fiber corresponding to the base point P now. And you have the following long sequence. So, of course, X naught is in this set. Maybe for this one I will write the whole thing. So, this map, first map, it comes from the inclusion of F in E, and this map, it comes from the map P over there, and the boundary map, this is something that requires some investigation, and it actually comes from long exact sequence of pairs. So, I won't go into those little. Basic idea is, if you have a fibration, then the relative homotopy group of E with respect to F is isomorphic to the homotopy group of P, and you replace the homotopy group of P correspondingly to get a long exact sequence like this. Okay. Now, what we have to do, we have properly look. Now let us look at some relation between homotopy groups and homology. Okay, before erasing this part, so what do we mean by stability? Like, I've started it off, but I haven't never mentioned what stability means. So, in homology theory, you might have seen that there is a suspension isomorphism theorem. So, if you have got a space S, the suspension and corresponding homology groups are isomorphic. But in homology groups, you don't have that property. So, in stability, what we mean is things. So, this is sort of a vague way of saying that stability means things that remain invariant under the suspension isomorphism. And we will get to it in a few minutes. Like what does it exactly mean? I won't erase that board. I will need it some time. So, yeah. Relation with homology. So this is something I think you have to take for granted. So if you have the reduced homology theory, be it singular, simplicial, whatever you like. So the homology groups of Sn, they are simply set in case n and 0 otherwise. And we have got the suspension isomorphism. So hk of x is isomorphic to hk plus 1 of suspension. What this does is, so if you consider S naught, so let I naught be a generator for this. Then under the suspension isomorphism, this generator I naught will go back to another generator of Hn. So basically, if you define In to be the suspension of In minus 1, so if you define it inductively, then this is a generator for Hn of Sn. Now what we can do is we can define a map from the homotopy group of the space to the homology group of the space. So you define this map, this is called the Fruedenthal map. So you start with your space X and you want to define a map to the homology. So what are elements over here? Elements over here are maps from the sphere to X. So choose any representative X from X to Sn. Now you consider you apply the homology function. So Hn of X. This is going to be a map from Hn of Sn to Hn of X. And what can you do? You can simply plug in the generator and this will give you an element in Hn of X. And this is the map we want. So this map that is called the Fruedenthal map, and what can be shown is that is a group homomorphism and it satisfies the natural condition. So if you start with space X and a space Y, you have a map between them, pi n of, and that will give you a map in their homotopy groups. And you have the Fruedenthal map that goes to Hn tilde of X, and you have and the homology functor will give you a map between the homology groups. So this diagram comments. What Fruedenthal theorem says is more is to go. Fruedenthal theorem. You start with a n-1 connected space. So say X is n-1 connected. And then the Fruedenthal map, it is going to be an isomorphism if n is, so the Fruedenthal map H from pi n of X to Hn tilde of X is isomorphism n is strictly greater than 1, and in the case of n equals to 1 and n equals to 1, it induces an isomorphism into the so pi n, pi 1 of X, the quotient of, so these are homology groups are always abelian groups, so you can factor it out through the abelianization, and this will be an isomorphism. That's basically what the theorem says. Good. So these two results, the long exact sequence and the Fruedenthal theorem, those are sort of the most elementary tools we have for computing homotopy groups of spheres. Okay, you might ask, why do we care about spheres? The thing is, spheres are the most elementary object that we can come across in topology. So there is a result which says that any space is homotopic to a weakly homotopic to a CW complex. And we know CW complexes are made up of attaching this along the boundary. So if you are able to understand what sphere, how the homotopy to the space looks, we can sort of make sense of what in general what would happen. So, some examples. Let's start with the simplest of case we can do. So, what about the homotopy groups of S1? So, this is something that is I think well known, that it is Z if K is 1, and these things are going to be trivial if K is simply greater than 1. The idea is you use governing of S1. So, governing of S1 is just real line, and we have got any map from the sphere. So, if K is greater than 1, any sphere is simply connected. So, you can lift that map, and since it factors to a contactable space, so this is going to be n. This group is going to be 0. And what about the other case? So, phi k of Sn. Let us think about it. So, using Homotopy's theorem and some sense of this is something you should know. So, Sn, it is the suspension of Sn minus. So, using Homotopy's theorem and knowing that fact for S1, this is this guy, you can show that it's going to be 0 if K is strictly less than n. It's going to be Z if K is equal to n. But after this, we don't know. In general, we don't know anything, like there have been various attempts, but we still haven't found a systematic way to study this thing. So, to give you a brief history, like there have been various times, like Pontryagin tried to compute for K equals to n plus 1, and we won't see the result, but we will see what tools he used to compute those things. So, Pontryagin had done it for K equals to n and n plus 2, and later Rocklin, whose advisor was Pontryagin, so he had shown for n plus 3 also. But really, like making breakthrough in computing homotopy groups is really difficult, because most of the things that we come across, it requires some new tool. Like after Pontryagin work, the work was completely stagnant for a long time. Then Sedet used some algebraic results to extend it till. So okay, so just to make things, let us denote this by K n plus K. So K is going to be our variable. So Pontryagin did till n K equals to 2. The student did it for K equals to 3, and later Sedet did it till K equals to 9. So those requires a lot of machinery, and after that it was again stagnant for a long time until Toda came up, and Toda showed some new tools, and he did it till 19. So it is really a difficult problem. Works are still being done. Like the main problem is we haven't recognized the pattern in it. So that's why any breakthrough requires a new tool. So it's very difficult problem. And with that, okay, I should have done that almost now.
What's the last question you said?
Toda. So, okay, we can look at some examples like the Hopf vibration. If you have seen, it will give you that so first non-trivial example where we want this guy. So the Hopf vibration tells you that the third homotopy group of S2 is Z. So maybe I should quickly go over it. So just give you an idea how this thing is. So the Hopf vibration is a very natural tool that was used to, like it can be used to do compute homotopy groups in various other cases, but we will just consider this one. So if you have got S2n plus 1, this sits inside Cn plus 1. And you have got the Cpn comes from quotienting out this guy. So Cn minus 0. And if you look at those, you have a natural map from Sn to n plus 1 to Cpn. And if you look at the fiber, these are just S1. And what Hopf did was he showed that this is a fiber bundle. And then you use the long exact sequence for this guy. So if you use the long exact sequence, we have got pi n of S1. Okay, so we will consider only the case n equals to 1. That is enough. So S3 to pi n of S2. And so, and this is a map coming from the of fiber. Now, if n is greater than or equal to 3, you know this guy and this guy are trivial. So this is trivial and this is trivial. Then this is a long instance. You get this is an isomorphism, and thus just plug in n equals to 3, you will get that pi 3 of S2 is set. Now let me come to the main thing. So the idea of stable homotopy theory, it comes from this theorem. So Fruedenthal theorem, that earlier mentioned that homotopy groups, they don't satisfy the suspension isomorphism, but what Fruedenthal showed was up to certain x they will satisfy. So let x be any n minus 1 connected space. Oh. Now you have got pi k of x, and you have a map. This is a suspension map. It goes from pi k plus 1 of x to suspension of x. Basically, you start with any map f over f from sk to x, and you suspend. So this will be your map from sk to suspension of x, but this is simply sk plus 1. So this is the map. What Fruedenthal showed was this is an isomorphism. If k is strictly less than 2n minus 1 and is surjective, if k is equal to 1, and after that we can't check. So using this, what we can now do is the following. So this is something we can show, that if your space X is n connected, then we will suspend it enough time. So say X is say minus 1 connected, and try to show that sigma k of x, this is n minus 1 plus k. This is something you can try out. So it will mean Fruedenthal theorem. Now using this to say k plus n, and you consider the n times suspension of x. Okay, and this other map to pi k plus n plus 1 to suspension of x. Right? Not there also any restriction of k or not k is out. You don't need anything. So this is true for anything. It has nothing to do with Fruedenthal. This is just using Fruedenthal theorem. So you have got this map. When will be an isomorphism? So this is going to be an isomorphism. This is isomorphism. If so, our index is k plus m. It should be less than 2n minus 1. But what is the connect? So this is n minus 1 plus m connected. So we want 2 times n plus n minus 1. And we just do the basic computation. We will get that what it is. M is greater than and greater than this minimize function hopefully different. So this is an isomorphism when the n is large enough. So what this tells you, this system, so you will keep on applying the suspension, right? So you will get to pi k plus n plus 2 n plus 2 of x, and so on. You can keep on doing that. So what this tells, the Fruedenthal suspension theorem tells you, this system, it will eventually stabilize, and that is the main idea of stable homotopy theory. So you define the stable homotopy group we will denote, so the S denotes the stable one, and N will denote the term we want. So then this is called the nth stem of the stable homotopy group. We define this to be, we take the co-limit by n plus k. So Fruedenthal theorem tells you that that thing is going to stabilize eventually, and then you can make sense of this. So actually you don't have to compute the co-limit. After a certain time it will eventually stop, and that is going to be your stable group. And what we are interested in is the stable homotopy groups of sphere. So we will denote it by pi n of s, and like since the suspension of spheres will give you spheres only, it is enough to compute the stable homotopy groups of S0. If you know S0, then you can find out anything. So pi n of s, this is the notation we generally use. This is simply the nth stem of the zero. And what is it? So this is simply the co-limit over k by n plus k. And suspend the zero sphere k many times, you simply end up with f. And if you plug in the value, so we know for exactly what value of k this group are going to stabilize, right? So if you plug in all those values, so S0, n is going to be 0 because S0 is not even path connected. So and n is 0, and you just need to find the k. And so if you are working with the nth stem, what you need is this k to be greater than, okay, I should have changed the notation over. So bear with me with that. So m, treat m as k and this as m, whatever, and n is going to be 0. Okay, maybe I should go just now it makes sense. Yeah, yes sir. If you plug in n0, you need m to be greater than okay, k is n over there, right? Because we are computing the k step. So this is simply pi 2n plus 2 of s n plus n plus 2. You need that to stick together. Okay, so that is the stable homotopy group. Now let us look. So I've kept this board for such a long time. So if you look at this table, let's start with your favorite. So let's start with the zero stem. Start with the zero stem. So you know from pi 2 onwards, this group is going to stabilize, and that's what this coloring actually says. So S1 of pi 1 is also there, but the suspension over there won't be an isomorphism. But from S2 onwards, this is going to be an isomorphism, and it is there. Now, if you look at say some other examples, so how long can I do that? So pi 4. So the first stem, so n equals to 1. If you look at the n equals to 1 stem, you have to start from pi 4 of S3, and if you look at pi 4 of S3, it is Z2, and n is still there. And that's what this diagram is. So that is the heart of stable homotopy theory, and what we will see now is how this thing is related to great stuff. Like this is completely an algebraic topological thing. Like this is, you are essentially doing algebra. And now what we will see, this problem of computing the stable homotopy group it reduces down to solving problems of classifying manifolds. Like if you have seen some things like Miller has shown that if you can compute the stable homotopy of sphere, you can sort of compute what are the exotic spheres you have. So exotic spheres are the things which are homotopy to sphere but have different differential structure. Let's talk about this. Okay. Some remarks. Okay, so just passing by, I don't think this will make sense at all, but still. So the notion of stable homotopy gave rise to what is called spectra. So spectra. So say you have a okay. Let me just go through the definition. So spectra is just going to be a collection of spaces with some structure map with sigma n. So sigma n is just going to be a map of E n suspension of E n to E n. That is what spectra is. Like we can take this to be the definition quantum. So if you have a spectra, you can define what are called, you can still define that system, right? And the suspension map, we will we have to use the sigma n to give the structure, to define the system. So once you define the system, you can then define the co-limit again. So basically, what you can define, so this is, let me call this to be E. Then you can define what are the homotopy groups of spectra. So you define the homotopy group of spectra to be this co-limit by n plus k. So we get n homotopy group as E. And the structure maps are coming from this. So why did I do that? Well, for the moment it won't make any sense, but another way, so given any space, we have a spectra. So we just keep on suspending the thing. So we have got that is sort of called the suspension spectra of that space. And if you look the homotopy group of the suspension spectra, those are simply the stable homotopy group of that space. So we will need it at some point if we can go there. Few more remarks like okay. So this thing, so pi n of s, you can define it for any n, and what you can show is this forms a graded ring actually. So you can define what is called pi star of x. This is simply to take the direct sum of pi n of x, and this is a graded ring. The way you define those maps. So say you had a map f and g. Okay, so this is in pi n of f, and this is in say pi m of f. Then you can choose suitable representatives such that f is from Sn plus k to Sk, and g is from Sn plus k to Sk. Choose k is sufficiently large enough. Then we can define f times g. Okay, just before that. So suppose one of them is larger. So then what you can do is you can suspend g n many times. So you will get a map from Sn plus k to Sn plus k, and then you apply it. You go to Sk, and you consider this composition. So f times g, you define it to be the homotopy class of this map, and g. So take k sufficiently large enough, then this guy is going to be pi m plus n. So that gives you the ring structure on this thing. Well, that being said, I think we can go into the next few things. So I had intended to talk about this thing. we are running very long. So now we will talk about cobordism. So cobordism basically means, so if you have got two manifolds n-dimensional, we say they are coborded if you can find another manifold of n plus 1 dimension such that the boundary of that manifold is m n. So say m and m dash are n-dimensional. Okay, we want compact and closed manifolds. So manifolds without compact. Closed and compact and closed. Then and suppose they are in some ambient space R and both of them. Then you say they are cobordism, then they are cobordism if there exists a W which is n plus 1, so W in R n plus t plus 1, n plus 1 dimensional, such that, so what we want is it contains some trivial or some polar neighborhood. So the reason we want this is to make arguments similar, nothing. So n dash for some epsilon greater than 0 and del of W is simply n plus 0 n dash plus. So our picture would be see? Give this one moment the definition. So now I can say M was this here, circle, so whatever. You consider a corner and say this was your M dash. You consider another corner. So they are cobordism if you can find a W such that W contains these two guys and the boundary of W is simply the discontinuity of M and M dash. Now what we will do is we will talk about framed manifold. So, definition, we say M in R and plus K is framed if the normal bundle should be like that. So I will denote my nu of x to be the nu to be the normal bundle. So and this is the bundle map. Also yeah. And you know what the trivial bundle is. So you want this to be the map does not be an isomorphism with the trivial bundle. So if B is your trivialization, then you say M comma B is the frame manifold. Now we want to classify frame manifold up to frame cobordism, and what does frame cobordism mean? So the idea of cobordism is you keep on changing the definition so that whatever properties you want, you get those. So frame cobordism is, so say you have got two frames manifold, so M and M dash M comma B and M dash comma B, these are frames. Then they are frame coordinate. If there exists a W in R equals 1, with respect to which they are coordinate, with respect to which they are okay, frame, so there must be a frame, so let me call it W comma with respect to which they are coordinate, and you want the trivialization, so this one G, it should restrict on to trivialization of B and B dash. Good. And G restricts to the trivialization. B and B dash. So if you have a look at that diagram, so this was the space, and say you had so normal bundle, you can think of the orthogonal part of the tangent bundle. If you have got your say your normal bundle or something like this, what you want is you can give using the normal bundle of M, you can give a normal bundle to this guy as the column neighborhood of M. And W comes with a normal bundle, and this guy trivializes. So what you want is the normal bundle coming from M and the normal bundle in W, they should trivialize exactly the same. So like the trivialization of W should restrict onto the trivialization of this part. Now, so cobordism forms the equivalence relation. That is something that you can observe. So obviously, it satisfies the reflexive property. You just take the cylinder on the space, and if you have got symmetry, it is also obvious because same W will work. And if you have got two, so say M is coordinate to M dash and M dash is coordinate to double prime, then because of the presence of this column neighborhood, you can glue them nicely enough, and the differentiable structures remain still smooth, and you get an equivalence relation. So we will denote by omega and F in. These are going to be cobordism class, so frame cobordism. Classes of n-dimensional manifolds. Closed and compact is we are dealing with closed and compact manifolds. So this is a geometric object. You can. What is the class? So you have got manifolds, you have got frame manifolds, and you view the equivalence of frame cobordism as equivalence relation. You consider the equivalence sets over here. Okay. Now this is the key thing that we will talk about. So Pontryagin, and Thom did it. They were doing it simultaneously over there. So Pontryagin and Thom. So the remarkable result is this geometric object is isomorphic to the homotopy group. So this is a completely algebraic topological result, and this is a completely geometric result. So Thom-Pontryagin theorem it relates these two results, like a geometric problem into a algebraic topology, it's an algebraic problem, and both of the problems are difficult. But that is what we do. We just reduce one difficult problem into another difficult problem and be happy with that. To give you an idea of the proof, so I won't go over the proof, but let me just give you the construction. So what is the construction? How do you even get framed manifolds? So we talked about a set, but what are elements in that set? It could be empty set, then this guy would be triggered, but they are not. So the idea is to start with a map f. So say f is in by n plus k of fk. So now I'm going to use some results which are quite elementary results in differential topology, but okay, yeah, sorry, I should have mentioned it. Really. So on the disjoint union, this forms a loop. If you have got two spaces, we can consider the disjoint union, and the framing would be just restrict the framing on each of the components. So yes, under disjoint union, this forms a loop. In fact, let me just explain it further. So this in fact forms a graded ring again. So you can take a sufficiently large enough, because if it trivializes in Rn plus k, then it will trivialize in Rn plus k plus L for any L. So what we can say is, so we can forget about this Rn plus k. Then over here we will end up with the nth stable stain. So just to tell you, so this will induce an isomorphism from. So forget about the ambient space. You get a map isomorphism between the stable nth stable stem of the homotopy group of sphere, and this will in fact give you an isomorphism between the. So you can define so the graded ring structure is just Cartesian product of manifolds. So Fn of R, and this guy is going to be isomorphic to by f of n, and that is simply as we had defined earlier, the ring I. Okay, let's come back over. So you start with a map f. Now, Whitney approximation theorem says that if you have got a element in K or in the homotopy group, you can replace it with a suitable smooth map. And the smooth map we want, okay, another thing. So we will view Fn as the one-point compactification of Rn. So you replace F with a suitable version of it. F is smooth, and F of infinity goes to this you can do. So you replace with a smooth map and then you apply a rotation so that infinity goes to infinity. Now Sart's theorem will tell you that the regular values of this function is going to be dense. So you apply using Sart's theorem, you know that this function has some regular value. So let P be a regular value of F. Then you know that F inverse P, let's call this M. This is going to be a n-dimensional manifold in Sn plus k. But since infinity is not in the pre-image of P, so we know that this is a manifold in R n plus. What? So you start with a map F and this is from Sn plus k to Sk. Okay. So M is an n-dimensional manifold in Rn plus k. But what is the frame? You want a frame. So the regularity will in fact tell you, so if you have M over there, every point of M goes to the point P. And P, so if you look at the tangent space, so since it's a regular map, what we know is dfx from tx of s n plus k to tt of s k. So x is any point in M. This map is surjective, and the kernel of this map is simply tx of M, because every point in M goes to the point P. Now, if you so this map, then it will induce an isomorphism. So dfx induces an isomorphism from tx Sn plus k to txm, a quotient of txm, to tt sk. And this is precisely our normal one with that m. Right? And you choose a fixed oriented basis of this guy, which you can do, and you take the inverse image under this map, and that will give you, okay, so I should have mentioned that earlier. Okay, I have written that. So, oh no, it is it. Okay. So, framing means you have got utilization, but in other words, what you can say is you have got k independent sections. So, or in other words, you have k linearly independent sections. S1, Sk from M to the non-functor. Okay. And that will give you a framing of kx of x, of M. But you have to take a lot of things. So first of all, what are the choices we made? We made a choice in the point C, and we made a choice in the coordinate, the oriented basis. So you can see that those things are going to be invariant to whatever choice you make, and a good reference for this is going to be Milner's book. Like as always, so Milner presentations are as trivial as it can get of a as non-trivial result as it can. So you can look at Milner's book. So Milner's book on differential topology gives a very nice explanation of that result. Okay. Where should we start? So using this Pontryagin-Thom result, what Pontryagin was able to do, he was able to compute the stable 1 step and the stable 2 step, and later Rocklin used this result again to prove it for stable 3 step. We won't go over it. But to end this talk, I would like to say, like, why should one expect such a result? So that is something, because it is a geometric object and you are relating to an algebraic object, and it should have some. So this is what mathematicians do now. We find some non-trivial ideas, we solve a very good problem, and then we are so humble that we want to show the world that, see, that was obvious, it wasn't that was difficult. So to give you the idea, so let me, how much time do I have? 10 minutes? So we will talk about generalized homology. So generalized homology are just extraordinary homology theory, meaning that they satisfy all the axioms of homology theory, but the dimension axiom are not like. So you can define a homology theory as follows. So say M comma F is a singular. Okay, I'm sorry. start with any space x. So let x be any space of each term. Now you say m comma f is a singular n manifold if f is a continuous line. So this is sort of, we are trying to generalize the idea of singular homology theory. In singular homology theory, you have a fixed n. You have the simplicities and you consider continuous map. And in this case, we will consider n manifolds, say f from f is a continuous map from m to s, and you consider those as singular n manifolds. And now you have so you can define Cn of x to be collection of all singular n manifolds. And you can define a boundary map. So we have got this boundary map from Cn of x to Cn minus 1 x. So you have got m comma f over there, and you simply map it to the boundary of m and f restricted on boundary of m. One more thing, so the empty manifold, in general we assume it is a negative dimensional manifold, but in case of cobordism theory, or what this is actually called cobordism theory, we will assume that the empty manifold is of any dimension. So because then n can be empty manifold, so we will assume that it is of any dimension. Now this gives you a complex because we are considering manifolds which don't have corners. So if you apply the boundary operation again, it will be the empty set. So an empty set, okay, so why even that is a complex? Like if you consider this guy over there, we have the operation of disjoint. So of course the empty manifold is sort of the identity element which we want. So we have got this map delta, and now you can consider the quotient. So you can consider the kernel of del n as the image of del n. What is it here? It's simply the singular n dimensional manifold, and the identification is done as follows. So you say m comma f is equivalent to n comma g if there exists a w comma h such that del of w comma h is simply m determinant n f. So I think you can see that. So you are quotienting by that, and this is a group. This is in fact an abelian group, and all the elements are ordered 2 in this. Why did we define this thing? So one more thing. So this defines the generalized homology theory. So those are functors. This defines a generalized homology. But why did we talk about it? So if you now look at the homology group for the point, single point, what is it? So now f and g are, so if you have a single point, there is only one map from any manifold. So basically what it boils down is you are identifying manifolds up to cobordism. Because f and g, they are, so this condition, last condition is to be satisfied. What is basically it is the boundary of W to be same as M disjoint union N. And you have got N D. So you are classifying manifolds up to cobordism. So this is simply omega N. This is cobordism class of N dimension manifold. Now, using Thom had proved those results in 1950. But in 1960s, Brown came up with his theorem of Brown representability. So Brown representability theorem says that if you have got a contravariant functor from CW complexes to sets, if it satisfies certain properties, those are representable. In particular, you don't need to go into the details of Brown representability theorem. Just assume that cohomology functors are representable functors. And since they are representable functors, using some duality theorem, so this requires some work, what you can show is any generalized homology theory is represented by a spectrum. So, this is a theorem. Any generalized homology theory and 0 is coming from spectrum, is coming or is represented by some spectrum, by some spectrum, say K. What this means is En of x, this is simply going to be pi n of k smashed with x, and this means you are just giving like the case point. So any homology theory is represented by the homotopy group of this spectrum. So K is a spectrum and you smash it with X disjoint in a point, and that remains the spectrum. So this is what the result we are concerned over here. And using that, this is due to Brown. So using this thing, since this is a generalized homology theory, we can define, so let's keep that code also. We will define it. So this is a generalized homology theory. It comes from some spectra, and that spectra, the Thom had proven it in his PhD paper that n of x, this is simply isomorphic. This is an isomorphic. Whatever. So this is isomorphic to pi n of MO. So MO is the Thom spectrum, and it is Thom. So now if you replace a point x with so if you replace x with a point, this is just the cobordism group. This thing is isomorphic to pi n of MO of x plus is just a point, and you can show that if you have a suspension of a space like this, so suspension, so this is S0 simply, right? This guy is S0 and smash it, you will get simply M4. And that is what the result is. So then, since this is true for all n, you can show that this guy out there, it is isomorphic to it is isomorphic to So over there we have seen it is the stable homology of PA, but in general you have got this result. So this I think wonderful result over there. Yeah, last remark would be to Thom had thought of those ideas, but he didn't know about bound representative theorem. He had independently shown that this is true. But I think we should give credit to Poincaré also, because Poincaré was the first person. Like Poincaré had developed singular homology theory. Poincaré had actually thought about this thing, but he realized like, no, this is not working out. Because like at that time, cobordism theory wasn't there. Cobordism theory was developed by Pontryagin-Thom. So when he was trying to define singular homology theory, Poincaré was trying to use this kind of result, but he realized no, there is a lot of problems. So let's just keep M fixed, and he chose simplicity and he defined singular homology theory. So what I would like to say is, so if you are in a talk where you talk on algebraic topology, if Poincaré doesn't come up, then you are probably sitting in the wrong way. So thank you.
Any questions?
So one thing is that you told that pi and the nth stable sum of S, when we take direct from that you get a graded ring structure. What about other spaces?
Okay, so in general, you won't get a graded ring structure, but if your space, in case of particularly spectrum, if I go to spectrum, so if the spectrum is a ring spectrum, meaning that, so you categorize the properties of a ring into the spectrum, if it satisfies those axioms, then you can show that, so basically what you need, so to define a ring structure, what you need is a structure map that takes, so if En was in spectrum, you need a structure map that takes En plus Em to, so say rho of M comma N, that takes it to Em plus N. That is what we need. And for CS you have such thing. And that's why we can do that. And in general, if you have, and of course this map has to satisfy a lot of properties, basically the ring axioms that we want, then those will form graded rings.